So this work is a collaboration between our colleagues at Wuhan Institute of Technology, their industrial partner, Wuhan Pudi vacuum technology company, who helped with the deposition process of the coatings and provided the setup, Micromaterials, and me representing Manchester Met. So we are discussing the etching process, wafer fabrication, manufacturing processes in semiconductor industry. And in this process, typically you would use a fluorine plasmas to etch your silicon wafers. And the problem with fluorine plasmas is that they are quite nasty. They corrode your equipment, your environment, and with that the entire manufacturing process is contaminated. So as a result, of course, you would be interested in developing materials with high resistance to fluorine plasma etching to improve the durability, improve the environment of the process and the outcome, the output of the manufacturing process. So that's the motivation for the work, hence our interest in yttrium oxide coatings. This is not the first work by any means in terms of looking at this type of coatings for this application. Those coatings are recognized and accepted as coatings with providing resistance to plasma etching. What is new in this work is looking at different annealing processes and options to see whether there is any impact in terms of the etching resistance. So that's our focus in this work. So those coatings also provide thermal stability, which would be very welcome in this type of manufacturing environment application. And compared to other industry standard aluminum oxide coatings, they showed to be much more durable in this fluorine-based plasma. So hence again our interest in this specific coating systems. So I will go briefly through the deposition process of the coatings, mention about some characterization we've done, show you the initial etching performance results, and then move to the most interesting part, I guess, for this audience, which is nano and micro mechanical characterization of those coatings. So coatings were deposited by radio frequency magneton sputtering, and you see the table with all the 6 variants that we deposited investigated in this work. So basically what you need to remember that we looked at 2 different annealing atmospheres. So first 3 samples were annealed in vacuum conditions, and samples 4 through to 6 were annealed in air environment. And between those 3, there is a difference between in annealing temperature, 300, 600, and 900 for those variants. And the deposition conditions are listed here. So a quick mention to the industrial partner, the Wuhan Pudi vacuum technology company, who is a manufacturer or a number of magneton sputtering systems. For this particular study, our colleagues choose PD500C system, which you can see here, which was used for deposition of those coatings. Right, moving on to some characterization. Let me start with XRD results. So you can see 3 characterization outputs for the coatings, for 300 at the top, 600 in the middle, and 900 annealing temperatures there. So basically, with the outcome there, the annealing temperature the increasing annealing temperature causes the XRD peaks become more kind of pronounced and sharper, indicating perhaps a corresponding increase in grain size of those coatings. And indeed, if you look at the SEM images of those coatings, again, 300, 600 and 900, you can clearly see some evolution of the grain size for the coating variants. So moving on to etching process, which was done in ICP reactor. So after creating a vacuum, a mixture of argon and oxygen was introduced into the chamber, and then subsequently the fluorine gas was introduced for the etching purposes. So our colleagues distinguish here between etching, which they call chemical etching, and physical etching. So let me spend just a minute on that, on explaining what we mean by chemical and physical etching. So in terms of the three variants for etching, you have the same ICP power, bias voltage, pressure, and etching time. So the only variable is the gas environment in the chamber. So what we mean that by chemical etching is that we don't have argon at all in the chamber. So we don't have argon bombardment of the surface. So we don't have that, let's call it, physical interaction between the plasma and the surface. And this is in contrast to physical etching, where we have argon, but we don't have a fluorine gas in the chamber. So this is what we mean by chemical and physical, and of course the mixed etching environment is where we have all three gases, and we have competition between chemical and physical processes, and this can be kind of described or illustrated through this cartoon. So in terms of chemical etching, you have chemical interactions happening on the surface. You have your fluorine products. You produce your volatile products. You have reactions going on the surface. In terms of physical etching, it's very simple bombardment mechanism of the argon atoms and removal of the particles. And in mixed case, of course, you have those two processes taking place in the same time. So these are results for the etching process. So after etching process, we removed the high temperature Kapton tape to reveal that edge, which was then measured using a step profiler, so that we can establish the depth of etching achieved, and with that we were able to calculate the etching rate. So you can see the three variants of the coating for two different annealing temperatures, for three different cases of etching, and for comparison we also included some of the other materials typically used in semiconductor manufacturing process. So basically, broadly speaking, increasing the annealing temperature enhances the etching resistance of the yttrium oxide films. And that would be kind of main takeaway point from the first part, which is looking specifically at etching performance of those three coatings. Before I move on to mechanical characterization, it's also worthwhile looking at the AFM imaging and results of the surfaces. So before etching, this is the surface morphology that we start with, and then after chemical, physical, and mixed etching cases, we can see surface morphology altered quite significantly, especially in terms of the physical etching. The surfaces tend to be much smoother. So moving on to mechanical characterization, and starting with nano indentation and nano scratch testing. So for nano indentation, we ran two sets of experiments. We started with, let's call it classical nano indentation, so 0.5 micronewtons, 20 repeats on each indent to 50 nanometers depth. And then we also run multi-cycle, so-called load partial unload nano indentation, very helpful in terms of understanding the distribution, hardness, elastic modulus distribution in terms of depth. And then we run nano scratch tests in the 3-pass mode, well known to many of you, but I'll go through some fundamentals of that type of experiment. So, of course, the platform 5, the nano-test Vantage system was used here. We use Berkovich indenter for the nano indentation experiments, and a spheroconical probe for the nano scratch testing. So the nano indentation results, hardness, elastic modulus, H2E ratio. Just as a reminder, these are our six samples. So broadly speaking, samples annealed in vacuum presented slightly higher mechanical properties, and then looking at the 3 different temperatures, perhaps 600 degrees kind of peaks in terms of hardness and elastic modulus, both in terms of vacuum and air annealing. Typical results for multi-load, multi-cycle nano indentation. So starting with hardness, six samples there. Seems like one of them, sample annealed in 900 degrees in air, presented lower hardness going into depth, all the way to 660 nanometers. But with this type of experiment, this trend is quite obvious. So this is not a single point. You have 40 indents clearly showing the trend in terms of hardness as a result of depth. So that's the result we have for that sample. And in terms of elastic modulus, fairly consistent results around 155 gigapascal. So 3-pass nano scratch test. So just as a reminder, for your first pass, you go with a minimal load of 0.5 micronewton just to get the surface profile from the scan. Then in the second scan, you ramp up your load, and depending on the conditions, you can set the experiments to a depth, to a load that you want to achieve. And then again, in the third scan, you apply minimal load so that you can get a surface profile after that ramping load event. And you can also extract load and correlate that to friction. So just to show you some optical images of this type of experiment. So each of those scratches represent a combination of 3 passes, so low load, ramp load, and low load again. And just to compare 6 samples, 6 variants of the coatings. This is the representation of those samples. So I think all samples show a very brittle response, clearly looking at the images in this type of experiments. Perhaps there's less blistering on samples 3, 5, and 6, and these show stress relieving cracks if you look at them. So, looking at the output of the 3-pass nano scratch experiment, you can establish and you can start looking at some critical loads in this type of test. So, just to explain what's happening in this graph. So, the initial topography scan is hovering around 0 there, no damage yet on the sample. Then scan 2 under load is that curve, so we can clearly see the increased evolution of depth as a function of applied load, and we can also look at the friction behavior during that load ramping event, which is your red curve there. And then the third scan is here in the middle, so the residual deformation damage, which you can measure with that low load third scan. So then you can start looking at those curves and analyzing them, looking at the critical events, typically LC1, so some sort of cracking, first cracking happening, and then some more dramatic failures, and you can quantify them for each of the samples, and also you can look at the friction value at that point. Not much in terms of numbers for that particular set of samples, but overall very helpful analysis in terms of getting into the mechanical response of coating surfaces under this type of loading. I think we need to spend a bit more time and be looking at some more loads in terms of extracting some more data for those critical events. But in terms of takeaway points from this first part of mechanical characterization, we established that mechanical properties are slightly higher for the vacuum annealed samples. 900 degrees annealing resulted in surface cracking and reduction in hardness and scratch critical loads. Pretty much all samples have shown brittle response in scratch test, and there is some blistering except for the samples which showed stress relieving cracking. So in the second part of mechanical characterization, we looked at a relatively novel method proposed by Micromaterials, which is statistically distributed nano scratching testing. So here we decided to run tests, randomized scratch test at 100 and 125 millinewtons with 40 and 100 wide regions in terms of spread of those scratch tests. And then we decided to look specifically at sample 1 and perform some additional 100 scratch tests on that sample with varied loads and varied area, and you will see why we decided to do that. And in terms of the indenter, again we use the same indenter as for in the previous case, which was spheroconical probe, as for the nano scratch testing. So this is how you set up the experiment in the software. As I mentioned, we look at two cases, 100 and 125 millinewtons. However, in terms of results I will be presenting today, it will be 100 millinewtons only. So 4 samples, 4 cases, 3 annealing temperatures, so 300, 600, 900. First row is vacuum, second row is air. So very quickly we can see in terms of sample 1 to 3 much less damage than samples 4, 5, and then 6. And perhaps in terms of temperature also there's some variation, and less damage on lower temperature side than the higher temperature side. And also the optical images confirm that, and we can see sample 1 less damage than sample 3, and vacuum much less damage than air down there. So what you can do with this type of experiment, you can also look and collect your data in terms of depth as a function of number of parallel scratches. So in that case we had 10 scratches. So samples 1 to 3 grouped together, and samples 4 to 6 there. Again, very clear difference between vacuum annealed samples and air annealed samples. So sample number 1, if you look at that graph there and image there, performed best in this type of experiment. So we decided to put it to a bit more test and a bit more stress in terms of this type of test. and we decided to run 100 scratch tests on that particular sample, and we started with 50 millinewtons load and 100 wide area for those 100 scratches. So again, you can draw and analyze your results in terms of depth and friction coefficient as a number of parallel scratches. So for those loading conditions, you can see around 60, 65, you start inducing quite significant damage. You start observing some blistering, which is clearly recorded as an increase of depth and increase of friction. In the second case, we decided to keep the same load, but increase the area we cover with the scratches. So we moved from 100 to 300 width, if you like, of that testing area. So basically, we increased the area for the scratches to randomly, take place, appear in that space, and with that, you can clearly see much less events where you can see increase in depth and increase in friction. And of course, that part where you randomly generated more scratches, generated some cracks, and that was clearly recorded in terms of depth and friction signal. And in the last case, for this type of experiment, we decided to keep the same width, so 300 micrometers, but we increased load to 100 millinewtons, and you can see that completely changed the picture, both in terms of actual picture and also depth and friction signal. So very useful method, I would say. There is a lot you can tune in terms of the area you cover, in terms of loads you apply to characterize not only coatings but surfaces in general. So a few takeaway points from that part. So samples 1 to 3, which were vacuum annealed samples, showed better performance in this type of experiment, but critical loads in nanoscratch were more similar. And samples 1 and 2 specifically performed best, but still undergo dramatic failures after reaching critical damage accumulation. And the 100 scratch test, which I liked so much at lower load or wider region, were very, very useful to investigate behavior of those coatings in more detail. So this work is very much in progress. We are missing some key etching results for annealing in air, which of course will be very useful to compare with the mechanical behavior of those coatings. We are also looking at some other coating variants, multi-layered variants. So if you are interested in that work, I think we'll be presenting this at ICM CTF in a few weeks in San Diego. So with that, thank you, and hopefully I regain some time.